end up killing your grandmother, or why you guys acclimate to high altitudes in a false kind of a fashion. So to get you guys started with this first, and definitely photograph this when we're all done, but also try and draw it as we go along and we do this. We're going to be looking at a capillary bed in your medulla. This will be our capillary bed in the medulla. So we'll put the capillary bed over here. And then, what is blood mainly comprised of? Water. Plasma, which is mainly comprised of water. And we know we have gases being transported in our blood. So we're going to have that equation found in your capillary. So CO2 plus H2O, which is a plasma. We go to form carbonic acid. We can break down and disassociate into a bicarbonate ion plus a hydrogen ion. Can't tell if Keith was drinking that or snorting that. Okay.
There's a straw.
It's a straw, okay. All right, now, what is a capillary made up of? Simple squamous epithelium, otherwise known as the endothelium, right? So in your mind, you may want to draw that idea just to reinforce that, because we've got simple squamous epithelium here. Maybe put a few of them in here, just to really drive home that point. All right? Now, why am I driving that point home? What does that red line represent, do you think? The what? The phospholipid bilayer, the cell's membrane, right? And what's the other name for a cell membrane besides a phospholipid bilayer? Semi-permeable membrane. Why is it called semi-permeable membrane? It only allows certain things to pass through. What kinds of things cannot pass through a cell's membrane? This side of it was really quiet. Eliza, do you remember? Phobic, do they phobic? Hydrophobic things can very easily pass through because they're non-polar. Hydrophilic things cannot pass very easily. What kinds of things are hydrophilic? Boy, that need to know list before the beginning of 242 might be on an exam. I'm going to start motivating you guys.
Positive ions can go through.
No, they can't.
Or positive ions cannot go through.
Ions can't go through at all. That's why they need transporters and channels, right? Remember, polar things cannot easily pass through a cell membrane. Non-polar things can, because non-polar things are hydrophobic. But hydrophilic things, things that can be easily dissolved and transported in water, can't pass easily through a cell membrane. They need facilitated diffusion, like leaky channels or gated channels or transporters or pumps. Why am I hounding you guys with this? Are there any ions in that equation?
Yes.
Is there one in the very end?
Yep.
All right. Now, if this is the medulla, does anybody remember the name of the chemoreceptor found in the medulla? Central chemoreceptor. What's its nickname? What's its AKA? Why is it called a hydrogen ion sensor? You're doing good. Because it senses hydrogen ions. And I've got hydrogen ions right there, right? But it's not, that's not the ones that it's sensing. What? So, let's have you guys draw, those of you in the cheap seats, so maybe Kyle can see this. We're going to put a big hydrogen ion. We're going to put a peripheral chemo or a central chemoreceptor. Oh, that's too big. Whoa. Get them ready. There we go. We're going to put it right about here. This will be your central, right, chemo receptor. Going to put a receptor for hydrogen ions And we're going to put the name hydrogen ion sensor inside of this. And it senses hydrogen ions. Well, I just said it can't be this hydrogen that's in your blood because that is a hydrophilic substance. There is a cell membrane, which means hydrogen ions cannot leave the capillary very easily. But can CO2 cross cell membranes pretty easily? Yeah, because it's nonpolar, right? And otherwise, how would cells get rid of their CO2 and how would cells pick up oxygen? So CO2 and O2 can very easily cross through cell membranes. So let's look at how CO2 can very easily diffuse into this environment. Well, if this is the medulla's central chemoreceptor, this is actually an environment of CSF. Remember what CSF stands for? Cerebral spinal fluid. Okay, let's get those 241 cobwebs shaken. What is CSF mainly comprised of? Not plasma, it was made from plasma. Water. It's mainly comprised of water. So I've got CO2 going into a fluid comprised mainly of what?
Water.
And what's going to happen when CO2 gets into that fluid mainly comprised of water? You do that equation all over again, because that'll be your source of hydrogen ions. And that hydrogen can come way over here. And that hydrogen can attach to your hydrogen ion sensor. And if you have an increase in hydrogen ion binding, three circles means therefore increase in hydrogen, that's redundant, write the word ion. Hydrogen ion sensor, and I'll get out of the way so you guys can see this. Stimulation, which leads to an increase in respiration rates. All right. Hydrogen ions go to the hydrogen ion sensor, which is the central chemoreceptor found in the medulla. As more hydrogens bind to the sensor, right, increase in hydrogen ion binding, therefore this sensor is stimulated, and the more it's stimulated, the more you breathe. And we saw that in that graph about pH values and respiration rates. All right, and I'm going to sort of do reality checks. Is everybody okay with that part of the idea? Yeah? Okay.
What the 3 circles?
That means therefore. Shorthand for therefore. Okay. Now, let's talk about that CSF. And what structure makes cerebrospinal fluid? Choroid plexus, very good. And what cells within the structure actually make the cerebrospinal fluid? Ependymal or ependymal cells. Gold star for Derek, right? He gets a whole bag of M&Ms for that. Okay? So let's reinforce that idea. Right? So here, this is going to be the capillary of your choroid plexus. Remember, the ependymal cells surround this capillary. So we're going to draw some choroid plexus cells. They are kind of cuboidal-like in shape. And we'll just put some cells and some nuclei in here. All right, and this will be an ependymal. And then we have blood here, So that'll be blood. That's in there. So we know blood is mainly plasma. So as the plasma in the blood goes into the ependymal cells, they filter it, and out comes cerebrospinal fluid. And that creates the mainly water idea, which is where this comes from. Now, there is a condition known as hypercapnia. Which is, I'll put it over here so we can do it again, right? Hypercapnia. Chronic increases in PCO2 levels. If you do not say chronic, I won't give you full credit. It's like if you didn't say tachycardia is a resting heart rate above 100, you just said increase in heart rate, it didn't work, right? Because this is a very important idea. If Zach just held his breath, right, his CO2 levels will go up. It doesn't put him in a state of hypercapnia. He just has elevated levels of CO2. It has to be chronically, we're talking months, or at least many, many, many weeks. So let's show that over here and see why this is an issue. If you have an increase in CO2 in the blood, how does that actually lead to an increase in respiration rates? Well, we know in the blood it leads to an increase in hydrogen ions in the blood, but we also know that CO2 in the capillary can diffuse into my medullous tissues. So that increase in CO2 will lead to an increase in the CO2 in my medulla tissues. What is that going to do to the hydrogen ions I have in my cerebrospinal fluid? Is it going to lower them or increase them, Kara? You know, if I get more of this, what happens to the level of hydrogen ions? Yeah, awesome. Yes, it does. Right? So we're going to get more hydrogen ions. All right. If you have more hydrogen ions, what happens to your pH? It's going to go down, right? And that means you're becoming acidic, right? And we don't want to become acidic. So I need a way of buffering that increase in hydrogen ions. Well, we know ependymal cells make cerebrospinal fluid, that's their job. We know they're filtering plasma to do this. But they also have a secondary rule, that if they are exposed to chronically elevated levels of hydrogen ions, they will, in response, start to generate bicarbonate ions. And then your chemistry brain should start kicking in going, I have a bicarbonate and I have hydrogen ions. I bet those little buggers could join together. So I could buffer the level of hydrogen ions. Follow?
This is in response to the increase? Decrease of,
well, you first started to say increase.
Is it increase of CO2?
Well, not really. I could expose them to increases in CO2. They're going to go, yeah, so big deal.
Okay.
It's the increases in this.
The hydrogen ions.
The hydrogen ions, all right? And due to the increase in hydrogen ions, the ependymal cells start creating a bicarbonate ion, and that bicarbonate can join with that hydrogen. So now we're going to get the bicarbonate plus the hydrogen. So now the hydrogens are going to go here. And what happens when you join a bicarbonate with a hydrogen ion? What do you get? You get carbonic acid because we're simply just going this way in the equation. So now I've got carbonic acid. We're going to stop there for a moment. This hydrogen, right, is this hydrogen right here. If that hydrogen hooks up to a bicarbonate to form carbonic acid, can that hydrogen go to the hydrogen ion sensor and simulate it? No. That means you're losing the signal to breathe faster in a response to an increase in CO2. Now, what will carbonic acid become? CO2 and water, right? All right, so then that'll become H2O plus CO2. Can CO2 cross the cell membrane? Yeah, and so that CO2 can maybe go into your blood, which helps to further increase your arterial CO2 values. What we're noticing then is with this hydrogen binding with bicarbonate to form this, put a little asterisk here, bring the comment down over here, right? 3 little circles, that means therefore, right? Therefore no response, no, I'm not saying no, that's say decreased response, that's a better way. Therefore, a decreased response to increased levels of PCO2. All right? Therefore, decreased response to increased levels of CO2. And if you don't get an increase in respiration, you're probably running low on oxygen. This is what happens to people who go to high altitude and they have a hard time acclimating. They're generating lots of CO2. That CO2 diffuses into the cerebrospinal fluid. That CO2 combines with water, which leads to the production of hydrogen ions. Normally, those hydrogen ions would go to the hydrogen ion sensor and you breathe faster. That's what happens when you first get there. And you notice your breathing rates are faster. But if you stay there for a while, a couple of weeks, and you have chronically elevated levels of CO2 because you've been in chronically elevated altitudes, this starts to become a problem. So the ependymal cells start to produce a bicarbonate ion because now you have a higher concentration of hydrogen ions, which lowers your pH. And anytime you think about lowering pH, you're thinking acidic. Anytime you think about being acidic, think about enzymes, which are made of proteins and denaturing, and not able to do their jobs, right? And so we need to make sure we don't have a drop in pH. So the bicarbonate could hook up to the hydrogen ions. It won't do all of them, but those that it does, those hydrogen ions won't be able to go to a hydrogen ion sensor. So you're getting fewer signals to cause you to breathe faster, normally. So what you get then is someone with high levels of CO2 and lower than normal respiration rates, because they have not yet fully acclimated to high altitude. So they normally give you then is oxygen, right, to supplement your inability to physiologically respond to the increase in CO2. Josie?
So when you're acclimating to levels of higher elevation, is there long-term effects? Like, because I mean, people live at higher levels of elevation, you know, everywhere around the world. So is hypercapnia just like this scenario where? Sorry, I'm having.
It's okay, it's right. So it'll happen like if you were to shove me up on Mount Everest, the first several days there, I'm going to start breathing faster because I have elevated levels of CO2. Right? That means I'm generating more hydrogen ions in my medulla. Right? That means more hydrogen is going into the hydrogen ion sensor. That tells my rhythmicity center, breathe faster. At the faster rate I breathe, what happens to my CO2 levels? They begin to go down. But if I'm there for a really long time and I haven't acclimated properly, I'm going to get a buildup of CO2, which leads to a buildup of hydrogen ions. Not everybody will do this, right? But it's also one of the explanations for someone who does experience hypercapnia due to high elevation levels for long periods of time. You're going to want to give them oxygen to supplement their breathing. And that could actually kill them. Because right now, this central chemoreceptor is not responding to the elevated levels of CO2. And what's the other chemoreceptor you guys have? The peripheral. And when does the peripheral kind of kick into gear? With O2? Low O2? Significant drops in O2, right? If I have elevated levels of CO2, you probably have low levels of oxygen, because they are like a teeter-totter. And if I'm chronically low or chronically high in CO2, I'm probably going to be chronically low in O2. And that means your peripheral chemoreceptors will kick in and help you to breathe faster. But
people who live at high altitudes don't suffer from hypocapnia? Like
not all, some do.
Correct.
All right. Normally what's going to happen though is you're going to increase your red blood cell production, you're going to increase your oxygen carrying capacity, right? You're going to hydrate more, so your blood volume goes up, red blood cell goes up, hemoglobin content goes up, your ability to carry oxygen goes up, and you're hunky-dory fine. Some folks don't do that. They fall into this category. All right? Let's see if we can begin to look at the consequence of that. Do I? Yeah, we'll do that. All right. Yeah, Zach?
I have a question.
Yeah, I'm listening.
So is hypercapnia consider only when like the epithelial cells start producing HCO?
Nope. Nope, not at all. Because we're going to introduce another way of hypercapnia here in a moment. Okay. All right, so now we're in the capillary in your, by your aorta. All right, so now this is from your peripheral chemoreceptors. I think I have enough time to do this. So this will be your peripheral. Chemoreceptor. All right, let's try this. So this is a peripheral chemoreceptor. You have O2, VO2 in the blood. Don't forget you have your endothelium of your capillary. We know that O2 can very easily experience simple diffusion through the tissues, go to the cell, and O2 can go into the peripheral chemoreceptor. In the membrane, you guys have a chemical gated potassium channel. And now we have O2 inside the cell. Remember, when it's gated, that means it can be opened or it can be closed. O2 is like the key, and this is a little bit different. Normally we talked about chemical signals coming to the outside of the cell and knocking on the door from the outside. This is an intracellular signal in a sense, within the cell. And O2, when it does attach to this receptor, right? So chemical gated potassium channel with O2 binding opens. Chemical gated potassium channel. So we'll show it looking like right here. Is there more potassium inside or outside of the cell? More potassium inside. When potassium leaves the cell, what happens to a cell's membrane potential? It becomes more negative, right? Okay. So let's walk through this again. Peripheral chemoreceptors respond to O2 in a normal fashion. When O2 comes to a peripheral chemoreceptor, the O2 can bind to a chemical gated potassium channel, and with that O2 binding, it opens the chemical gated potassium channel, potassium leaves the cell, and therefore MP becomes more negative. And everybody's okay with that idea? Okay, now, so what was it that caused the potassium channel to open up? Oxygen binding to that chemical gated channel. Now what if, we're going to do it in blue, we had a chemical gated potassium channel, and there was no O2 binding. Can potassium leave that cell? No. Well, that's good, all right, that's correct. So what if you had a decrease in potassium, a decrease in O2 levels in the blood? That means you have a decrease in O2 coming to the peripheral chemoreceptor, which means you have a decrease in the number of O2s attaching to the potassium channels of the cell. What you want to keep in mind is that there are lots of these gates in a cell membrane. And when an O2 comes in, it may not be attaching to all potassium. This is like statistics. It's a random chance idea. But if I have lots of O2, I'll be attaching to lots of potassium channels, lots of them will be open, and lots of potassium leaves. But if you have fewer O2s, then fewer of your channels are going to be opening, more of them are going to become closed or stay closed. Does that idea make sense? Right, with a decrease in O2, you'd have fewer potassium channels open. What is that going to do you think, to the membrane potential if there are fewer gated channels open for potassium to leave through? It's going to become more positive, right? Because there's less potassium leaving. So when these are closed, so therefore chemical gated potassium closed, the inside of the cell starts to become more positive. And in that membrane, I'm going to put it right here, you guys have another kind of a channel, one that you're very familiar with. It's a voltage-gated calcium channel, just like you do on synaptic knobs of neurons, right? What makes a voltage-gated calcium channel open? Voltage. What's another name for voltage, maybe, do you think? Membrane potentials. So if that membrane potential becomes positive enough, we can open up these voltage-gated calcium channels. Where's there more calcium, inside or outside? Outside. That means calcium is going to come in. And what do you know about calcium coming into a cell? Where does it usually tend to bind to, besides troponin? So how do you guys release neurotransmitters? How does exocytosis take place? Do you remember?
Next to the vesicle.
Calcium binds to the vesicle to allow the vesicle to release the contents, right? So if I have more calcium out here, and we'll go through this again on Monday, baby. If calcium can come into the cell, they can bind to a vesicle, a neurotransmitter vesicle. And there's going to be neurotransmitters in here. Here's my calcium binding to it. That can then go to exocytosis. And that means we're releasing neurotransmitters. Neurotransmitter release. I'll get out of the way in a second. Therefore, increase respiration rates. All right. O2 can come into a peripheral chemoreceptor. When it does, it binds to a chemical gated potassium channel. Makes the potassium channel open, potassium leaves the cell, and anytime, one of those rules I'm trying to teach you guys, anytime ions cross cell membranes, two things must come to your brain. What charge is on the ion, that'll affect whatever membrane potential I've got. And then of course you gotta have pumps to put the damn thing back where it belongs to, which we're ignoring. Potassium leaves the cell, making the cell become more negative. If the cell's more negative, can we open up voltage-gated calcium channels? Nope. And if we can't open up voltage-gated calcium channels, can calcium come in? No. If calcium can't come in, can we have exocytosis of neurotransmitters? No. Which means we're not going to increase respiration rates, right? Well, that's fine, because we've got oxygen coming in. But now, what if you don't have enough oxygen coming in? Keep in mind, it's sort of like this row of chairs here. Not every single chemical-gated potassium channel will have an oxygen binding to it. So it's more about how many of each do I have. If I start getting more chemical-gated potassium channels without having oxygen attached to them, those doors won't open up. Which means more potassium than usual stays inside the cell. Which means the cell becomes more positive. If the cell becomes more positive, right? So therefore, let's complete that thought. Therefore, the cell becomes more positive. That means voltage-gated calcium channels will open. Calcium follows facilitated diffusion, lands on vesicles that are inside the peripheral chemoreceptor. Those vesicles contain neurotransmitters, which would land on neurons that make you breathe faster. Which makes sense because you were low on O2. That's why we ended up having to open up voltage-gated calcium channels in the first place.
What's the neurotransmitter called?
Doesn't really matter. It's glutamate, I believe.
Where's it go?
Respiratory center for your brain. All right. Now, does that last part make sense? And we're going to revisit this last part again on Monday. But now here's the thing. So John gets a burr up his butt, goes to Everest. First couple of days, he's breathing faster, but he's not breathing fast enough.